Hi everyone. I'll be talking about our paper, The Price of Selection in Differential Privacy. This is joint work with John Ullman. Understanding the limits of privacy is a very important question. The question is how many statistics can you release and what kind of statistics can you release with what accuracy? Our problem is called the top case selection problem. You have a data set of plus minus ones and n samples from the data set. You can think of the data set as a high dimensional data set where the number of attributes D is much larger than the number of samples. And the question is how do you release the k most important attributes of this data set where k is much smaller than D privately. So here the k most important attributes are the ones with the highest mean. Our paper gives optimal lower bounds for this private selection problem. In particular, we show that when the number of samples is smaller than k log D, every algorithm which releases these k, just the coordinates of these k most important attributes is blatantly non-private. So this was a notion introduced in the seminal work of Dinur and Nassim on reconstruction attacks. So I will briefly introduce differential privacy. The main motivation is that no adversary should be able to distinguish should be able to learn about a particular individual of the data set. So basically you have, let's say, two data sets which differ in exactly one row. A randomized algorithm is said to be differentially private if its output on these two data sets so its output distribution is closed. So the private selection problem, as you can see, is a very simple problem to describe, but it has many applications. For example, in sparse regression and hypothesis testing, etc. So I will define the private selection problem more rigorously. Basically, you have a population on plus minus 1 to the D, and your data set is n samples from this population. Q of x is its true mean, and the problem is to release a top k set T of x such that for every coordinate in T of x, it differs from the actual top k mean by at most alpha. Our result is that when the number of samples is smaller than k log D, then every algorithm which outputs this top k set T of x with accuracy alpha equal to square root log D by n is blatantly non-private. And this holds even when P is chosen to be the uniform distribution and the algorithm outputs this T of x with an alpha accurate T of x with high probability.
I have a question. I'm confused. Here you have T of x, which is 42.56, and then there you have T of x, which is a subset of the integers. I'm confused of what T of x actually is.
So T of x is just the set of coordinates, like it's a subset of the attribute set. And every coordinate, the mean of the coordinates in T of x differs from the true top k mean by at most alpha. It's a set of
just some two indices.
Oh, two indices.
Yeah. Sorry. So let's go back. So we showed that when the number of samples is smaller than k log D, outputting the T of x with high accuracy is violates privacy. So this result is in fact optimal, because when the number of samples is bigger than k log D, there is a differentially private algorithm which outputs this set in with high accuracy. And we are interested in this accuracy regime because this is the sampling error when X is chosen IID from the population. Our main technique is tracing attacks. You have a population which is a uniform distribution on plus minus 1 to the d, and X is a uniformly random data set from this population. An attack basically takes this top K set T of X and a target individual Y, and outputs whether Y is inside the data set or outside the data set. So basically the attacker gets a top K set T of X, target individual Y, and when Y is randomly chosen from the population, it should output out, and when it's a random member of the data set, it should output in. So this in fact violates privacy, and you can show that it violates differential privacy. So if you show a tracing attack for this top K selection problem, basically you get a DP differential privacy lower bound. The attack is very simple. You just need to take the sum of the target coordinates, where Y is the target individual. You need to take its sum over the top K coordinates and check whether it's above a threshold or below a threshold. So I'll give a quick analysis overview. When Y is randomly chosen from the population and T of X is an alpha accurate top K set, we get that with high probability it is above this threshold of square root K. So this is because since X and Y are independent, the expectation over these coordinates, so the sum is the sum of the expectations, and it turns out to be 0. And you can also convert it to a high probability statement by using any concentration inequality. So what happens in the case when Y is a random member of the data set? So basically the top K the mean of the top K coordinates is highly biased. This is a key fact we use, and that's why when you take its expectation, this expectation is above this threshold of K square root log d by n. And even though in this case X and T of X are not independent, we can show that it concentrates around the expectation. So therefore, when Y is out, and therefore we have these two statements, that when Y is out, it is above this threshold, and when Y is inside the data set, it's below this threshold with high probability. And you can actually distinguish between these two cases when the second expression is larger than the first expression, basically which boils down to K log D being bigger than order of n. And therefore you get a tracing attack for this case. And hence, since tracing implies a differential privacy lower bound, we get that when the number of samples is K log D, and you cannot release the top K set with high accuracy. Thank you.
Within which there are the top K. So you are asking you just output the K plus 2 size set that contains the K top. Will it still be violating privacy?
But that is implied by the alpha accuracy, right?
Because I don't care about how far are the last
Oh.
two.
I think a modification of the analysis would work for that.
I think there's actually a harder problem. Like it's easier to prove lower bounds for that.
Anyway, you can discuss it. Any other questions?